SwayamPrabha. Digital India. Educated India.
Welcome back. We're going to start a new topic. It's called mass and energy analysis. So in the earlier, we already looked into the energy analysis of a closed system. In this case, we are going to take mass and energy analysis for the control or open systems. So we're going to work on the control volume. So this is the learning objective of this particular lecture. We're going to develop the conservation of mass principle and specifically apply it to various systems that include steady and unsteady flow control volumes. Okay. So let me summarize what we have done earlier for the case of closed system. So for closed system, the general energy balance can be written as relation okay. So this is specifically the general energy balance for the closed system. Now what we want to do is to extend this analysis for the case of a system where flow, there is entering of the flow and as well as exit of the flow from the system, and hence the energy analysis will be for the case of control volume. Okay, so let's try to develop conservation of first mass principle. So we are going to control volume. So this is, let's say, our control volume, okay, which is inside your this dash line. Okay, so this is my control volume, and then you have series of streams which enters from one side, or in general it enters and indicated by this arrow. So this will be your in, and this would represent outstream. So in general, we are going to write your energy or your conservation of mass by writing a general expression which would be that rate of change of mass, okay, within the control volume should be equal to rate of mass in, okay, minus rate of mass out. Okay, this is of course there is no term on the generation because mass cannot be created or destroyed. That would be the system which we are going to consider would be true. So in general, we can write this expression in mathematical form by considering the mass of the control volume as mCv. Okay, so this will be your change in the mass of the control volume, and the rate of change of that, this should be equal to effectively whatever comes in terms of dot m dot, that will be rate of mass in minus rate of mass out. This would be a specific relation, but if there are many streams, then we can write this as a summation of all the rate of mass in due to different streams. So this will be sum over this and so forth, and similarly for the case of mass out. Okay. Now how we are going to define the total mass of the control volume? So total mass within Cv. Okay, so we can consider a small volume here. Okay, so this, let's say, is a volume, and the mass of this particular volume we can consider it to be dm. Okay, and this would be volume, would be corresponding volume would be dv. So we can write the expression of the total mass of volume would be a simple integral of this small box over the control volume, which essentially means we are integrating over dm over Cv, which essentially can be rewritten as in terms of the density and volume. So let's assume that the density here is rho, okay, of this particular small volume within the control volume. So this would be your rho times the the dV, the volume of the small box here. Okay, so this will be the expression of the mass of the control volume, and thus you can plug this expression back in this equation. Okay, so now let us also consider small differential area component on this particular control volume. Okay, so this could be a small differential component here, which will be area. Okay, let us say the flow which comes out from this particular area is represented by this velocity here v, and the normal vector could be, let us say, your n here, which is n vector. The angle between them would be your theta. So in other words, we are considering a small differential area within this control volume, and the flow is represented by this v dash, which is a velocity in this direction, and the corresponding your normal vector to this differential area would be this n vector here. So the angle between them is represented by theta. Okay, so n vector is this is a unit vector, normal to, let us say, this area is dA, so this is dA. Okay, and your velocity is the flow velocity. Okay, so what about the mass flow rate for this particular system? So the mass flow rate would be nothing but rate should be proportional to the normal component of velocity. Okay, so let us define this as a Vn. So Vn would be your V cos theta. So now it depends on the theta itself, like whether if you have a component which is perpendicular to the differential area, then it will be the maximum flow rate. If it is a parallel, then there will be zero flow rate. If it is 180, then it is actually inward. Okay, so depending on the theta, one can consider it to be outflow or inflow. So this theta could be 0, so this will be your maximum outflow. Okay, if it is 90, then it is a 0 outflow. Okay, if it is 180, then it is a maximum inflow. Okay, so now we can consider the differential mass rate. So the differential mass rate essentially means what the amount of mass which comes out from that differential area would be represented, let us say, by dot here, which will be rho times the normal velocity times the differential area. So the reason is that we are considering the density here, and this would be the volume. So this can be further as rho times Vn can be written as V cos theta dA. Okay, so if you integrate the differential area over the surface of the control volume, you would get effective net mass flow rate. So which essentially means that you can calculate your net mass flow rate by integrating over the control surface, which means on the surface of this control volume, okay, which essentially would be your rho V n dA. Okay, now this essentially has also the component inflow and as well as outflow. Okay, because what you have done is you have considered, let us say, the regions which are inflow and as well as the regions which are outflow. So when you are integrating over this, you are also considering the different thetas associated with Vn component, and hence you have the net mass flow rate, which includes the inward and as well as outward flow. Okay, so the direction is already accounted in this expression. So now we can use this information to come up with the final expression for the mass conservation. So let us write that. So we have already written this. This is our expression. So we can replace this m Cm by this expression and m dot in by this expression. Okay. Now instead of taking the overall control, we can say this is effective in and this is the effective out surface area dm. or this would be the direction. So hence we can separate these two directions and this divide into these two directions such that this can be written as separately in this following form. So you have your d mcv by dt, okay, sum of m in minus m out, okay, dot here. So now we can write it as d by dt, the control volume, okay, rho dv, and this would be your sum of rho vn dA minus sum of rho. There should be integral here, so this will be for a specific area, and we are saying this to be, if we use this expression, this will be your in and this will be your v and dA for the specific case of out, okay. Okay, so this is my the complete balance based on the expression what we have written, rate of mass in minus rate of mass out, okay, that will be the rate of change of mass within this system. Let us consider the fact that your velocity need not be constant across the cross section, and this may also change with time. We will just consider a case of a pipe, and then we will consider, like, we are aware of the flow profile of the fluid within the pipe. So we will try to understand that can we replace this variable velocity across a cross section by a average value, and this is what we are going to consider now. So a typical pipe can be considered as this parallel lines here, and the flow profile would be something like this, okay. So here if it is so which essentially means that the velocity in the middle will be highest. So this is the overall profile. Now this is more cumbersome to make use of it because you need to know the profile expression across this cross section, okay. And in this case what would be more useful is to find out the average velocity. So this average velocity would be, so if we say this cross sectional area is AC, this would be your, okay. So this is your average velocity, okay. So what about the mass flow rate through this entire cross section? The mass flow rate would be through the entire cross section of a pipe, okay. This would be your m dot dm, which now we can write in terms of if we write the general expression as we have done earlier, then this will be this, but now we can replace this expression by rho v average AC. So this would be your mass flow rate. You can also rewrite in terms of the volume flow rate. This expression can be written as your rho times v dot, where this is your volumetric flow rate, okay, where v dot can be written as, or it is by definition the velocity multiplied by the differential area across the cross section. We integrate, and this is what we can write as v average AC, okay, or v times AC. Okay, so this was the general mass balance. We are going to apply this mass balance for the state process. So let's look at what are the conditions which we are going to make use of it. So what we are going to develop now is your mass balance for a steady flow process, okay. So considering the steady flow conditions, the total properties within the control volume is going to be constant over time. So thus your mass of the control volume should not change, which essentially means the derivative of the mass with respect to time should be 0. So total mass within CV does not change, okay, which essentially means your d mcv by dt should be 0, okay. Now this is a straight it's obvious here. Now we can simply make use of this particular expression in our mass conservation principle. So what we get is the following. So your dmCv by dt, we know this is now written as m in minus m out, which should be 0 considering that this is for a steady flow system. So which means your m in, so that the net mass flow rate in should be equal to net mass flow rate out. Okay. So for the case of let us say we can illustrate this using an example. So you have a system with let us say 4 inlet. Okay, so this is your control volume. Okay, now these are the inlet and this is the outlet. So this could be your M1, M2 dot, M3, M4, and this is M5. So based on this expression, considering this to be a steady flow system, can be written as M1, the inlet R, summation of this M dot in is M1 plus M2 plus M3 plus M4. This should be equal to the outlet, summation of outlet mass flow rate streams, and this will be M dot 5. So we have now developed this expression for the steady process. Now many applications just involve single streams. Okay, so examples are nozzles, diffuser, turbine, okay, compressor, and pumps. Okay, so these are the devices which involve a single stream. So we can consider a case for such a device. So this is an example of your air compressor. Okay, and this is your control volume. This would be your outlet stream, let's say is M2 here, and this is your inlet stream with M1 dot. Okay, so based on the single stream and steady flow process, we can write summation M dot in is equal to M dot out as simply in this case M1 dot is equal to M2 dot. Okay, now we can consider this is having density rho. This will have different density because it's an air compressor, is going to compress it, and the density at the exit would be different compared to what is at the inlet. Okay, and the cross sectional area will be, let's say, A1 and A2. Okay, so in that case if we consider the velocity here to be average velocity, so this would be your rho 1 V1 A1 is equal to rho 2 V2 A2. Okay, so if you consider cross sectional areas to be same, in that case this will get cancelled and rho 1 V1 should be equal to rho 2 V2. Now being a compressor, your rho 2 density at exit should be higher than rho 1. This would indicate that the velocity at the exit would be lower than at the inlet condition. So we can consider a specific case for this single stream steady flow process, and this would be your case of incompressible fluid. So for the case of incompressible fluid, your rho 1 is same as rho 2. Okay, which essentially means for the case of single fluid, your V1 times A1. So this would mean that your V1 times A1 should be equal to V2 times A2. In case of same cross sectional area, this would mean your V1 should be equal to V2 or if it is a different cross section area, which means this is nothing but your volumetric flow rate should be same for such incompressible fluid. Okay, so this would be your generic expression for incompressible single systems. Okay, for the case of a multiple streams, incompressible fluid would be, the expression would lead us to summation of V1 or V's for inlet is equal to summation of volumetric flow rate of outlet, okay, for different stream. So this would be the expression for the case of multiple stream. So with that we will come to the end of this lecture, and in the next lecture we are going to apply the energy principle for the case of control volume, and we'll develop the expression, and we'll discuss specifically the total energy of the flowing systems. Okay, so we'll see you in the next lecture.